results we have. Yes, so today I would like to give you a introduction to concept of service mesh. I will talk about this. We have this subtitle: opportunities, obstacles, and sidecars. Um, and I really want to have this interactive conversation because I, you know things or two about service mesh, but I really want to learn through the questions, maybe from the audience, what kind of challenges currently they have, or what kind of. Oh, perfectly! I start getting some responses. Yes, some people using this in production, some people using or evaluating those, but also there's a few people who are not planning. If if you can go to chat and just type down, if you're using this in production, what kind of product do you use, or whatever you're using for this, or also um, if you not planning to use or not using service mesh or not evaluating or not interested, just let me know at least a few reasons why not. That would be great to understand. And yeah, so that will give me a um, great understanding of the where the audience are coming from. Okay, see Istio. Some people using the Istio in development. Okay, good stuff. Okay. All right, cool. Even some people use Conk. I believe it's probably Conk Gateway in this case, and Istio in production. Okay, so I see a majority of the people using Istio these days, and it's not very surprising for me to see, uh, simply because Istio is quite popular. It's was one of the project that had all the marketing power of Google to get promoted, and there are a few companies who providing a commercial support for Istio as well. Maria, can you run the second one just to understand what kind of like a stack of technologies people are using? Just where we're coming from development perspective. So personally, I came from Java background, but I'm very much the polyglot right now. Writing some Go codes um, for Clone Gateway plugins, a little bit Lua, a little bit Lua anyone. And yeah, if you are not using Java, Node.js, Ruby, Go, what do you use it for? Like, what kind of microservices? What you use to develop your microservices? That would be a very cool thing to learn. What do you use? And again, if you see not if you don't see response that would be aligned with your field of interest, just write down in the chat. Okay, I see some of the polyglot, JC Murray, kind of polyglot, everything is there. Node.js, .NET. Okay, yeah, always keep forgetting about .NET. This is also quite popular. Um, nice. A few more people .NET. Cool. All right. So I like to talk about service mesh as is something that supposedly will help us to simplify our architecture for applications. Like I mentioned, came from Java background, and a lot of things that I learned being in the Java world is to build monolithic applications. We used to have application servers, and application server is essentially something where some of the piece of application infrastructure, if you may, and you will see why I started from this, and we're calling out some of the old architectures, and when I will be talking about new architectures. Now, so with the monolithical application, there will be application server. That's something that you as a developer programming against. It will have some of the capabilities of the web server, so you can program some web part, but also it will include some of the things, some APIs that allow you to program against databases, Say you need to extract data, write data into database. You need to implement some business logic and maybe sprinkle a little bit of messaging things. And essentially, this architecture gives us infrastructure where we were deploying our applications. Many people, for example, .NET, I see many developers using .NET like Internet Information Server. It's another example of old ways of building monolithic applications. ASP.NET, ADO.NET, and these days everyone's writing microservices and maybe using some other frameworks right now. You're not building against the good old application server. But the good old application server provides you with certain pieces of infrastructure. For example, you don't have to hard code or configure database configuration. In the Java world, we have this Java it's called JNDI, Java Naming and Directories interface, that allows us to get access to database connection through some sort of naming. So this piece of infrastructure provided me a discovery service. I don't need to know database host. I don't need to know where to find this. It will provide this to me. Same thing with the maybe messaging system. Another thing is that it also provides some basic observability. If you ever program against this kind of system like application server, you usually can get information about the request times, request latencies, all these things you can extract from application server, because application server provides you a infrastructure for running your apps. Definitely, it may be not super. Not many people can relate if you just writing like a simple web apps and you always writing microservices. But in my case, we have to refactor this, and this is how we ended up in the world of the in the world of microservices. We need to refactor this monolithic application. So, and we're going to be talking about what this refactoring brings us, and how the service mesh as a new piece of technology help to improve your application infrastructure. My name is Viktor Gamov. I work as a principal developer advocate in a company called Kong. At Kong, we build tools and everything that you as a developer needs to build this application connectivity, API management, API gateways, service mesh, developer tools. We're also developing a tool called Insomnia that allows you to develop and test your APIs. I am a former Kafka expert, so have lots of management and Kafka management expertise in the past, and also Kafka community catalyst. I'm a Java champion. Java has a big part in my background, and also I wrote a few books. One recent one is Batchy Kafka in Action, and a couple years ago I switched from this kind of like a data world into the more like a general cloud connectivity, cloud native connectivity, APIs, Kubernetes, and all this kind of stuff. Because the overall evolution of our software and software delivery, how we building our system, how we deliver our system significantly changed. And I found myself that this is quite fascinating. And there's places where we can optimize some of the work. But the microservices, usually when we talk in containers and we're talking about microservices, and we sometimes maybe not exactly right, but we use them interchangeably. Definitely there's some correlation, but I don't think it's a causality. However, the invention and the widespread of containers and the container orchestration, container management systems increased adoption of microservices architecture. And APIs is the way how those systems are communicating. When I talking to about this architecture, it's really, if I will say, can I put all this in container? Yes, I can. definitely I can put this in a container, but will it make it this microservice? Well, I mean, not entirely. So everything that this infrastructure provides will be just running container. Container will be just the way how we deliver an application. But I want to talk about communication and connectivity between different components. Many components in this architecture, for example, some of the front end specific things that were generated on the server that were solved by the server. So this is where this monolithical application actually has some connectivity because we need to deliver this to front end. Sometimes when we talk into this different enterprise being some business logic, some business logic, some of the logic the application does, those beans can be invoked locally or can be invoked remotely. And also connection to database, usually for resiliency, we don't want to put this in one place. So when even we're talking about monolith, this still involves connectivity. Like even if it's a monolithical application, we still have some sort of network communication through the system. And what we want to be is to bring this monolithical one thing that would be running all our applications into, we're decoupling this into multiple services. We're moving our computation from kind of like a in-process based, the things with my object called method, and after that, I'll get the access to the response, into the network base where the API becomes your interface of calling things, and the network and network connectivity becomes a essential element of our computation. Now, when I like to talk about network, usually network is the big scary place where multiple things can go wrong. Here's a few networking problems. One of my favorite memes, like a technical memes from this kind of like a microservices era, is a fallacy or false facts about networks. Just after we're done with this presentation, you can go and Google it. But essentially, it's like a 12 facts. One of the facts is that, oh, our network is super reliable. No, usually if something goes wrong, usually it's a network. It's a very rarely that there's like some bug in application code. Obviously, it's possible, but network usually causes some troubles. And network communications include network communication challenges and problems that might include like encryption. When we're running this as our monolithical application, we need to think about security because all the calls happen internally. And if you're using like .NET, if you're using JVM or some sort of runtime that runs your application, this runtime is responsible for providing you encapsulation and some sort of like a protection between some of the malicious code cannot, or some of the places inside your code will not be touched in other pieces of your code. With different how we can be running multiple versions of the same application, or like versioning of those APIs. We need to run the parallel environment with all blown application server. We need to run different version of database. All these things is challenging, very challenging. If you try to run multiple parallel environments and kind of DR environments, now you need to run all the services that you running those. How you capture and centralize, collect all the metrics, logs, and traces, all the things that your application require if you want to run those successfully in production. Like I said, previous infrastructure tools usually provide you with all this kind of information. Now you need to figure out how you can do this. Now, with with this with the communication between those subsystems, you might find yourself in a situation where the outage can cause, like network outage can cause a problem for whole system. You can lose connection, and your application will be down, and you will not be able to serve the serve the business. And most of the times it was never implemented. So all these things that will be taken care of, retries of the connections, and maybe sending some graceful message back to a API consumer saying, "Hey, yeah, I'm down, but here's cached response," something like that. Those things usually implemented when you start getting these outages, and you can have someone that's saying, "Hey, so this database is not super stable, probably we need to implement caching." So you implement the caching, so your caching not running as a part of your application, because in this case you need to work in with different trade-offs about memories and things like that. And those things needs to be part of your code, right? So every time you implementing this, or it needs to be part of some sort of infrastructure. And more applications you're running, more you're repeating yourself. And if I bring back to this diagram that can be potentially represent how different applications talking to different applications within the same one organization, but different department will have this. And every time when you need to write a resilient application, you usually either implement it yourself, or you're using some framework, or you implementing a framework and start sharing this framework across multiple departments, so the people will not have to implement this yourself. But so this is why I started our conversation with a question: what is your application stack? When you're running in the single stack, you can definitely organize and formalize the set of tools and set of frameworks that you're using for handling this type of situation with the resiliency, fallbacks, caching, all these things. But if you're running multiple stacks, if you're running this in you have someone mentioned that they use Node.js, Go, Java, JVM, so multiple different services written in different systems. You need to either find a way how you need to find a framework that has the same capabilities in Java and Go, which is, let's face it, would be unrealistic, or settle on some sort of like a common denominator that has okay support in one language and so support in another language. So what if this piece of repetitive code we can take out from our application? So no one have to implement this. No one have to implement this. All the things with the routing, security, and your stuff, logging and tracing. So we take this out of the application code and put this in something that will be taking care of this communication. So it will take care of the error handling, will take care of some of the security communication, and usually the proxy server, or any type of proxy server, or also known as a like a API gateway these days, can help solving this type of problems. If you ever done some sort of SSL termination on the proxy side, you know what I'm talking about. Like every time you need to have a secure communication between your API that your clients will consume in your server, you just implement this on the proxy side, and you don't have to implement this on the application side, because usually your proxy sits in the same network as your application, so you don't have to have a like secure connection between the proxy in your application. But it's not always not always the case. Now, and bring it back to this slide. So when we extract this code, we put this in the proxy, and those services will start communicate to each other, not directly, but through the proxy. So for this to work, this binary proxy have to be on the execution path of every incoming and outgoing request. So that's the proxy by definition. So that could enforce security, TLS termination, login, and other components that you want to do, any type of like a traffic shaping stuff. Also, since I mentioned, this proxy needs to be on the execution path of every request, meaning that it should not create much of the latency in order to solve the request, because in this case, it will defeat the purpose, right? So with the proxy binary, and this is important, it's not something that you're putting inside into your system or some framework. It's a binary that would be running with your application, will talk into your application through a local communication, so a local network. And regardless of programming language you use, it will have unified communication. So even important to bring in this slide again, one of the first generations of service meshes, and let me look into this in the chat. Gentleman named Ahmed mentioned that they use Linkerd as well, and this is how the Linkerd, the first version of Linkerd started. It was a Java service mesh, and it was the framework that you put inside your application, like a Java agent or Java library that runs with your application code. And after that, Linkerd version 2, they extracted this code and implemented binary that will be running alongside of application code. So with this, this communication becomes a much more unified, because you can write your code of any application, and this proxy will handle communication and connectivity between the system in a unified fashion. And also it speeds up application development, since teams don't have to worry about all this binary, because this binary will be always, doing the thing. Now, interesting enough, and this is where we kind of closing loop on monolith. Application traffic was there like even before, and the same kind of like approach with like calling one monolithic application against another monolithic application also can be path to modernizing your application by implementing this sidecar and communication, and start offloading some of the pieces of this functionality to this sidecar thingy. It's very my favorite piece of technology these days is Kubernetes. Deploying my apps on Kubernetes, I'm just doing this every day. It's so easy, and thanks for some of the cloud providers that make this leap super easy. And I just use managed services with Kubernetes cluster. I can spin up the cluster at will, deploy my apps, and make them ready to be used. But not many people like as I am. There's still people who use virtual hardware, like virtual machines, no Kubernetes, or even physical hardware, some bare metal. And in this case, it would be cool that this unified process also work not only in Kubernetes environment. So Istio, so many people, I make a very strong assumption. I will make this assumption that those people who mentioned that they're using Istio, most likely they're using Kubernetes as their a deployment place. This is where they deploy. Write down in the comments if I'm mistaken about this. So, and that's why the Istio becomes very popular. However, if you're trying to run Istio somewhere outside of Kubernetes cluster, it's possible, but you need to have experience what you do and deploy sidecars. How you configure those sidecars is actually quite challenging if you're not doing this in Kubernetes. In the recent releases, Istio has simplified a lot of things in terms of deployment. Many things possible to do, not in the Kubernetes way, but also you can do this in VMs and things like that. So that's important for many people, and I will explain why it is important for the project that I will be talking in a few seconds. Now we're going into the interesting world, so where the proxy also can solve the same same challenge, the same task that every proxy were doing. It's basically load balancing. How to have replicas of my service that running in whatever, like it's running at the virtual machine, it's running as an bare metal, running as a pod. But this proxy also can load balance balance the load between those services, and will do the same thing that the proxy does. And in this case, it can be one proxy per service if I'm talking, in this particular case, or and after that, like balance the load between different instances of the service. So you don't have to have like a one-to-one relationship between service and number of replicas. Now, it's all good, it's all nice, and so we have a proxies, and remember, we're running multiple services. Now we need to configure communication between the services, since we built some sort of I don't want to say mesh just yet, but we built some sort of like a network of our services. Now, in order to traffic flow smoothly, we need to update configuration. Many of you know that about configuration management, and since we are the platform engineering community, definitely like GitOps is one of the approaches for configuration management and like driving overall configuration of the systems. Now, but this configuration is good when we have a, say, some sort of like a static configuration is defined, right? So we have our static file in our Git environment, and once we did the change of this configuration, this static file would be delivered. But what about the runtime configuration? We need to have centralized place to control our decentralized deployment. So once we have more than 2 instances of our applications, or that is more than one, we'll already have a decentralized deployment. It can be problematic if you decide to change configuration and you need to restart those proxies in order to change this configuration, right? So this configuration needs to be dynamic. And it's good if you have some sort of configuration service that will be propagating those configurations into all of this configuration. So you can change how the traffic flows between these multiple different services by updating configuration on the centralized environment. And after that, this centralized environment will send this. Now, in a world of the modern application architecture, so those two things usually referred as a data plane, the ones that will be receiving these configurations and will be responsible for serving traffic, that doing the stuff, right? And a system that will be shipping those configurations, we'll call it control plane. So this control plane can be one-to-many relationship, or we can also think about architectures where control plane can be part of something bigger, like a multi-mesh architecture if you want, but it's we can touch this in a bit in a second. Now, with proxy, there are proxies are on the execution path. So data planes are a part of the execution path, but control plane is not. So control plane can be down for maintenance, or there would be partial network partitioning between data plane and control plane that allows to your system stay resilient. And since control plane is not on the path of the request, it is not single point of failure. So your data planes will be operating on the old configuration if control plane will be down. So once the connection will be restored, your data plane will get updated configuration and everything will be nice and fine. And this is how we basically invent a service mesh. So service mesh includes two components. One component is a control plane, is a centralized place that will be responsible for holding your configuration, holding your policies, and multiple data planes that you will spread out, and those data planes will be running next to your application, next to your workloads. So why we just few words about why we refer this as a sidecar. So right now, this illustration operates under assumption that this process have some sort of local connection to the service. This proxy process has a local connection to service, and in this is more like a generic picture of, or more like a generic view of the of our architecture. In the world of Kubernetes, where everything is opinionated and different APIs have a different notion, we usually pack those two subsystems into two containers that will be sit inside one pod. And in the world of Kubernetes, this is called a sidecar container. So essentially, you have a container that will be, but it's just I'm trying to explain that those separation of concerns between sidecar and the application containers, they are only conventional, because in the world of Kubernetes, there's no API yet that can mark one of the containers as a sidecar, another container as a main container, because there's no like a life cycle that can say that the sidecar needs to go down after the one container will go down. So think about this. It's just like the sidecar is just another container. And the importance of this is because inside the pod, inside of Kubernetes pod, sidecar and your container, all containers that runs inside the pod, they share local host, they share the network, and they share file system. They can share some of the volumes. So that's how some of the data planes can extract not only network information from your main container, but also some logging information and stuff like that. But anyways, I got carried away a little bit to talking. I was asked to like pay a little bit more attention on some of the the sidecar things, so that's why I want to talk a little bit more about this. Now, this is service mesh. Service mesh includes, once again, control plane that will be managing the brains of the operations, and multiple different data planes that's small enough, fast enough to receive dynamic configurations from control plane and establish a appropriate communication between the services based on the policies or traffic policies that were enforced through the control plane. This is, I think I can call it singularity, right? So this is how multiple different things came full cycle. So we using these proxy servers here in control plane that will be responsible for configuring those. The same idea was also designed. Oops. Same idea was also designed and implemented in decentralized deployment of API gateways and proxy servers. You can have some sort of like the air traffic control tower that will be responsible for managing multiple different proxies. And this idea was brought up into the service mesh world. So now, I mentioned this, that control plane can manage multiple data planes that deployed in multiple different locations. So you can have a global control plane that manage multiple meshes that will be deployed in the different environments. It can be different um, different things will be distributed across multiple different environments. And interesting enough that the each service don't have to go and have a many connections. Service mesh have a concept of egress and ingress that allows to manage how the traffic goes in and out, and some of the nodes have a little bit more responsibility for pushing traffic between multi meshes. And yeah, this is kind of like a combination of what usually refers as north-south traffic when you have communication from one place, from somewhere outside of your data center into your data center, and east-west traffic that happens inside your data center. Now, I am here to talk. So the thing that I just described, it's general knowledge and it's applicable to pretty much any service mesh that's available out there. There's at least 10 different projects that has a service mesh in its name inside CNCF in Cloud Native Software Foundation. And Kuma is one of the CNCF projects. Kuma, before Istio joined CNCF, Kuma was only project that used Envoy as a sidecar. So Envoy, it is a proxy server that developed in Lyft, and this Envoy proxy, super performant, super fast, small enough to be serving this the sidecar responsibilities. And Kuma represents implementation of control plane, how this developer will interact with this control plane and shipping some of the details into data plane, how the traffic would be configured. So that's it for presentation. So let me try to see. We can run through some questions, but meanwhile, I will try to set up this stuff inside my Kubernetes cluster, and we can see what Kuma gives us. I don't know if you folks want to ask some of the questions, but this is website. Yep.
No, I just wanted to say thank you very much for the presentation, and guys, start adding in your questions in the Q&A section, and I see one of the questions already coming in. If you weren't already going to cover this, could you explain the concept of service discovery and how service mesh supports it?
Perfect. That's a great question. So I will be trying also, like you still see my screen right now, right? So you see Kuma website. I will try to bring some of the example of my application. So let me quickly show you what I have, and I will explain all the things by example rather than doing hand waving stuff. I will show you how this usually works inside the service mesh. So let me do bigger screen here. And I just do bigger screen. So I have a Kubernetes cluster, pretty big, but you don't have to have this big cluster. Just like do multiple different experiments, and I usually over provision. And inside my namespace, I have this Kong mesh control plane. So it's a one pod that has one container called control plane. So let me see service, and I will just do expose the port. Expose the port. This one. And if I will go to localhost and I'll just do 5. Oops, 5. So first of all, it has API. So everything that I will be showing you also accessible through the API, but also it has a built-in GUI that allows you to see what is going on here. And by default, there's nothing is running. There's no control planes. There's nothing exciting. So, and by default, it has one default mesh, and nothing is happening here. I can see this is the just a mesh. Nothing is really here. Now, in order to start doing some stuff here, I have a demo application that I have here. I'll just do make, and I will just do install. Where's this guy? I forgot the name of this demo microservice install. Yep. Now, so I will deploy my microservice application into this namespace called boutique namespace. And what it will do, I'm lazy to writing my own application. So I just went in Google GCP microservice demo GitHub. So I found that many people who done this in Istio world, they use this demo, and some of the Google people actually use this demo. I just figure out, okay, so what? I'll just take their demo. I'm not gonna write my demo, and I'll see if this demo will work with any service mesh. And in this case, it's actually surprisingly it worked just fine. So if I will go to my microservice demo and I just run the scaffold, and I will just do this, delete, not delete. Boutique, and I will be using this one. And I will deploy those services here. Explaining the architecture of this application is beyond of this presentation, but it's good that they have a diagram here that explains it. It has a front end. Some of the application, different components of this system are available in different microservices. So what I will do, I just deploy this into this boutique namespace. And I will wait until these things will appear here. One of the things that you will notice is that I have 2 containers inside of each pod. So let's take a look, for example, on the front end. What we will see here, there's a server container that will be actually our front end application. And there's 2 things called init and the sidecar, Kuma init and Kuma sidecar. How the hell they appear here? So if I go to my boutique namespace definition, I will see there's annotation called Kuma IO sidecar injection enabled. So the folks who are replied in a poll saying that they use an Istio, they're familiar with this idea. An idea also came from, well, I mean, dependency injection, right? So you injecting a dependency, in this case, our sidecar, automatically. So the system control plane that sits inside your Kubernetes cluster, watching all namespaces that have this annotation. And after that, during creation of this resource, it will modify the deployment of this particular service and will inject one of the containers. So the way how it looks like, if I go here and I will list of deployments, say, for example, front end, and I will see this deployment. So what happened here inside the spec, it will put a container that will include this application container that will serve these things. But also, it will include a where's another container that will include front end. It should include another container. Containers. Boom, front end, server. There should be another because we modified this deployment. I guess we modified this deployment on the fly somehow. Now, and if I will switch to my UI of my Kong mesh, of the Kuma mesh, Kong mesh again is just installation of the just a version of Kuma. We built Kong mesh out of Kuma. And what I will see here, if I will refresh the screen, I will see multiple services, and all these services are coming here. Now, to the question of service discovery. Once those services are running inside a service mesh, they register. So since every data plane needs to communicate to control plane, those services are registered somewhere in a control plane. Now, each service will have a name, something like this, and inside this control plane, inside this service mesh, you will be able to address those service, or like find the service using this this kind of URL. Also, inside this things, where is it? Control plane pod by itself also provides DNS server, so you will be able to configure the service discovery using some sort of like a prefix. For example, by default, it has a prefix for .mesh, so you can have your services configured and referred inside the mesh. It's also useful when you have a multiple meshes that deployed across multiple different environments, and you will have a one common namespace. Because in this use case, it's very easy because those services are deployed inside same namespace. So that's why kind of referring one service in another service, it's fairly easy because this is how it's done. So each microservice has this currency service as a value that is injected as an environment variable. However, with service mesh, you will be able to refer the services within this service mesh by simply doing kind of like a .mesh and things like that. Do we need to configure the Maverick Me? Do we need to configure some extra things in the service mesh in internal services RGRPC rather than TCP, rather than HTTP? I'm sorry. Very good question. So the Kuma is smart enough to introspect a service definition for particular service and figure out what kind of port is. And Kuma supports auto discovery of this L7 protocol. So all these services, by the way, in this demo communicate to each other through gRPC. And only things in the past, I had to do something like this. Let me show you. If I need to go in microservice demo, going into Kubernetes manifest, I had to do something like this in the past. For example, providing some extra annotation that would say, okay, so the port 9555 will be actually gRPC. So in this case, it provided a hint for Kuma, but now it's not necessarily, because it will be able to introspect and know what if it's a HTTP2 protocol, most likely it's going to be gRPC. Yes, so the Arthur asking the question that I actually answered, and I will repeat one more time. So I'm not sure about the control plane architecture, but if we are centralizing traffic through this component, is it the single point of failure? If yes, how we can avoid this problem? Arthur, so control plane, let me bring this slide real quick. Yeah, so the control plane is not part of the request request chain or the execution path. Control plane is only responsible for keeping connection with data planes, and no traffic goes through the control plane. Control plane exists to shipping updated configuration back to our data planes. So control plane can be down, but your application will still continue to perform. So I answered this live. Okay, so let's see. Why Kuma didn't approach EPF approach rather than sidecar? So very good question. So, and this is rather longer conversation, and this is not entirely true anymore. So Kuma has a 2.0 release that includes ePBF support. For those of you who don't know what we're talking about here, so sidecar essentially, when we're running this sidecar thing, let me close this. So for example, let's continue with front end. I have a few things here. So one thing is that when this deployment will start, it will run init container that will configure IP tables on inside this post. So all requests will go into this sidecar, and only after the sidecar will route all the traffic to underlying server. This approach worked for many years, and I think it's going to be working for many years as well, because it is quite simple separation of concerns. It's not invasive. You don't have to mess around with anything. And this architecture would be universal. What does it mean? It is you run the same architecture with VMs, bare metal, Kubernetes, or whatever next big thing for container management will be next. Now, with implementing functionality of traffic routing, the problem with the IP tables in this case is that sidecar talking through the local host, meaning that sidecar needs to go through all this down the stack. You know, when we're talking to we need to talk to L7 to L7 communication, but it will go down the stack and back and forth. Generally, it is not something that will give you like a terrible performance or whatnot. No, it's a local communication. However, there is a faster ways. So the faster way would be avoid to sending this application in working on the user space, but rather have this network configured on the kernel space. And this is where this eBPF comes into mind, where configuration of how the traffic would be routed now will not be handled by IP tables, but handled on the kernel level. So this is where the eBPF comes into play. This is very controversial and very interesting topic for conversation. I wish we have this good old days when we have this after meetups. We'll go to bar and talking about these things in the bar, because this is exactly a topic whether you want to have a conversation with someone having the glass of wine or a glass of beer. Because it's very opinionated. Now, one of the concerns that I promised to talk about the service of the sidecars. One of the concerns that people have that this sidecar, it will be consuming a lot of resources, and this is valid concern. Don't get me wrong. I understand that once you implement in service mesh, you start doing the things like this. Your bill will increase because you're not only paying for your applications that you deploy, but also you're paying for the pieces of infrastructure. And those pieces of infrastructure, not something that you just, not giving you anything in return. So let me show you how I would implement some of the simple things that will take you probably some time to implement, but this will automate the process of let me show you how I can enable MTLS connection between those applications. So right now, if I go and see this like a TLS report, what it will do. So right now, communication between data planes are not secured. And this is another example of service discovery. This is also name of the service that can be discovered inside the mesh. It usually has a .boutique as a namespace, as a CNI. Now I will enable this, and we'll go and say, oops. Go in here to the mesh, and I'll just do kube control, apply mesh YAML. So what I will do, I just change configuration for this mesh to enable a certificate management. Now, apart from the other things control plane can do for you, now we learn that control plane can do for you is configuring data planes. It can inject sidecars. It can be a DNS server and provide the server discovery. It has a nice UI and stuff like that. Also, control plane can be your certificate authority. It's a built-in certificate authority. You probably want to use this for some sort of like a development purposes, and you want to integrate with third-party certificate authority, like, I don't know, Vault and so some other things, or like assert managers, whatnot. But by default, you have this ability. So you have ability to enable certificate authority built in and have a automatic certificate rotation after 1 day. Let's see how it will go. Now, inside this, I'll refresh all. Immediately, control plane was able to generate certificates that signed with the certificate of root certificate, ship those certificates to data planes. Those data planes updated configuration immediately. And after that, establish a secure TLS connection between each and every data planes. Now, those things can be implemented on the outside of sidecar. Probably yes. However, it's basically, so what the eBPF will give you, it gives you a programming interface, and you need to implement all the things on the kernel level if you want to have all these things. Even if sidecars will consume some resources, those resources are not something that you are just, the paying for. And it's actually do the job. They do the job of automating this stuff. And in order to push this down to kernel, it will create additional problems. Plus, for sidecars, to have a sidecar, your deployment is much easier. If one of your nodes your pods will go down, it will just like restart it somewhere else. If you will have a deployment of your, I don't know, the proxy per node, and one of your systems will be affected by this, you need to restart whole node, and all the application that runs on the same node also needs to be restarted. So it's really a thing about it, like a different trade-offs. So let me see what else, what kind of questions we still have. Okay, perfect. So how does this work in the multi-tenant environment where are submeshes and other policies? So the Kuma supports running this in a multi-mesh environment. You need to have a global control plane that will be controlling. Let me show you with this. And we go into deploy, no, multi-zone deployment. It needs to have a global control plane. It needs to have a zone ingress and egress in order to traffic goes from one zone to another. And each zone will have its own control plane in order to configure local communication. And after that, you will be able to define the policies, and inside the mesh, the services will be, they'll have their own service discovery, and the traffic will go in through the egress and ingress, all the things automatically once you configure. So for application code, it will be looking exactly the same as they will be running in one namespace. But from perspective of infrastructure, everything would be handled by combination of global control plane, zone control plane, zone ingress, and zone egress. Also, let me know if we're going to be doing any survey. Maybe some of you would be interested to learn more about multi-zone deployment. We can do like a follow-up webinar, or I can another thing that, like a shameless plug, if you didn't notice into my Twitter, you can see this is my Twitter thing down below. You can send your request about the what kind of materials you would love to learn more, and I do live streams at the Conk YouTube channel every 2 weeks, and I talking about all possible things, what you can do with service meshes, API gateways, and the Kubernetes and whatnot. What are the differences between console and Conk? Mohsen is asking. So, like I mentioned, if we go into CNCF, service mesh projects, we're gonna see projects, and there should be some sort of like 6 CNCF mesh tools that are available: Linkerd, Kuma, Open Service Mesh, Service Mesh Interface, Meshery, Service Mesh Performance. So, and now we have Istio also is a part of CNCF. It's also official CNCF project. So there's a bunch of other projects. So console is a console is a service mesh that is developed by HashiCorp folks, and based on some of the things that they built with console. Many people use console as a kind of like a service discovery system and the arbiter for different the metadata thing. So yeah, it's another service mesh that available there. I know that many people are using this for their environment because they came from HashiCorp ecosystem and things like that. So again, without going into much of the details, it's another service mesh implementation that has ups, like plus and minuses and things like that. So this is pretty much it. Okay, so let's see one last thing that we can also enable here in the service mesh. So one of the cool things is that there's a different traffic modification and traffic routes that you can configure. So by default, all communication to all the services is enabled, and every service can communicate to any service. We can have policies that will be explicitly permitting or explicitly denying the traffic, how the traffic will communicate and things like that. Another very cool thing that Kuma has is virtual outbound. Is basically having the program software-defined NAT type of thing. Some of the systems like Apache Kafka, for example, they have the certain requirements on how the network names should look like, and in order to run this and have this like unified version of this, the virtual bound like can create NAT rules for different services, or like for different replicas on one service that will appear discoverable inside the mesh. I actually did a service mesh con in Valencia, and I was talking about this functionality and how to run Kafka inside the service mesh. There are multiple different things that we can talk in future, or we can talk about, and I will be here I don't know what's our time limit, but I will be here until every last question will be answered. So,
No, Viktor, please don't. It was such a passionate conversation, but I'm sure that people have to work. But as a suggestion, we can move our passionate conversation to the platform engineering Slack channel, where you can start a thread, or just like whenever who still would love to hear more thoughts from Viktor, just hit him up on Slack channel. I'm sure that he will be very happy to answer those. And well, sorry about that. I'll be
absolutely. It's a perfect segue and a perfect opportunity for people to register for platform engineering Slack and continue conversation there. It's great.
Yeah, I'm sure that a lot of those they're already there. But thank you to you, Viktor, for leading a great session. Thank you, everyone who attended and who stayed till the end. We'll send over the webinar replay tomorrow. So if you missed a piece, don't worry about that. You will see it all together tomorrow. And thank you all. Hope you have a great day and week moving forward.
Thank you so much for having me. My name is Viktor Gamov, and as always, have a nice day.